Okay, so let's finally access some images that are part of the New York Times articles that are there. So the way that we're going to do this is eventually what we're going to do is I'm going to define this New York article with media class. And it's going to inherit directly from the New York Times article function. So all of the functionality that we had from using text inside of these articles is going to be retained. But inside of this New York article with media, I'm going to have a list of NY media objects, which we'll also define. So the NY media objects, or the NY multimedia object that we're going to define here, this class, it's really just meant to take the dictionary elements that are part of that New York Times multimedia list that we had right there, that were part of the JSON, and really save all of the images that we get back from the New York Times. So what I'm going to do is define this function getImage right here. And essentially, if self.image is equal to none, we're actually going to go out to the URL where the media should be located, so self.media at the URL, and we're going to read it in and save it into self.image. So now when we access getImage again out of self, it'll just return self.image, so it'll just return the raw image data that comes back from it. And so what I'm actually using here is the skimage module. So this is something called scikit-image, which essentially allows us to read almost any of the common formats from the web. So things like JPEG, PNG, GIF, so the GIF file format. All of those are readable, and we just have to provide it with the URL where it is to access it and download it. And so that's all that we're really going to do with this NY multimedia class is, if we haven't downloaded it, download the image and save it into self.image. And now we're going to use that inside of our New York Times article with media. And because we've already defined NY article, this is going to be a really, really intuitive and easy class to write. The only thing that we need to do here is add in a list of all the multimedia associated with this article. So we'll overwrite the initialization function from NY article. And the first thing that we'll do, because we're overriding that, is we'll call the superclass, right? So we're saying, okay, well, what is the superclass of NY article with media? It turns out it's NY article. Call the init function for that and give it the article data. So you remember before we needed to define all of that JSON data that was associated with it. And we'll just do that. We'll just give it the article data that's passed into us. We're also going to define these two new properties, which is the number of media that's inside of this article and a list of all of the NY multimedia instance objects for that. So essentially what I'm going to do here is say, okay, well, what's the length of self.data at the multimedia? But then also for each of the elements that's inside of self.data at the multimedia, so for each element in the list, make that into an NY multimedia object, which means I can call things like getImage on the element that's inside of this list. And I'll just create it as a list, self.multimedia. So if we want to, we can absolutely call, we can define a couple of functions, just convenience functions that we wanted to have here. So I can call the function getImages if we wanted to. And all I'm going to do here is I'm going to create an empty list of images. And for each element inside of self.multimedia, I'm going to say, okay, well, the image is equal to m.getImage, grab the image, and I'm going to append it to this images array and return the images array. So that's all I'm going to do here. I'm just going to exactly return the data. But we could have done something a little more interesting with that, such as called show images. So in this, for each of the elements that's inside of multimedia, I'm going to grab the image from it, download it if I haven't downloaded it, and then I'm going to call plot plt.imshow of the image right here. So imshow is part of the matplotlib article, which will actually take the image and just show it, and then I'll call plt.show at the very end. That's optional. You don't have to do that when running from a notebook. But we'll just do that with the very first article. So I'm going to say A is equal to a New York Times article with media, and I'll give it the very first element right here. And then I'll call a.showImages. So it'll go out, download the images if it needs to, and display them. So for the very first article, it turns out, though, here's the first image. It's a little blurry. You can see it's all blown up. The second image, this is a much more detailed view. So this is a higher resolution image. And the third image right here. So you can actually see that it's just a close-up of this part right here. So the way that the New York Times does their article and their images is essentially they have a low sampled, right? So this is a small image of the same content. They have a high res version so they can display it on whatever web page they want in more fine detail. And they also have a little itty bitty snippet, very, very small. It's 75 pixels by 75 pixels, which essentially you would use inside of if you had like a table view or something, and you just wanted a small icon description, this would be the icon associated with that article. And when you clicked on it, it would open up the high-res version, depending on your browser and properties and what resolution you had set. So that's the way that the New York Times saves all of the multimedia associated with this article. But there could be multiple images associated with this as well. So, instead of creating a new figure each time and plotting them, what if we actually wanted to just get all of the images that are there and do some of the plotting on our own? And in this way, what we're going to do here is I'm going to create a figure, which is 15 by 5, and then I'm going to call for each of the images. So I'm going to enumerate images. So I'll get the index and the image data for each of these images that I have, and I'm going to put it in what's called a subplot. So plt.subplot right here, what that actually allows you to do is make multiple graphs and put them inside the same figure. So what I'm actually saying here is, I want to subplot this where my subplot has one row and however many images by columns. So if there were 3 images, this would be a 1 by 3. And what I'm accessing here is I plus 1. So essentially what that does is it says, oh, okay, well, you've got a figure that looks like this. And I'm going to make it 1 by 3. So 1 row by 3 columns that we have right here. And now this is 1, 2, and 3. So when you tell me to subplot into I plus 1 right here, so we start at 0, right? So I plus 1, this would be 1. That says, okay, plot the first image into this subplot. And then plot the second image into this subplot, and the third image into this subplot. For however many subplots there are inside of this, it'll keep doing it for however many images are returned inside of that list. So we can actually do that, and I'll call IamShow on the image data, and then at the very end I'll call plot.show. So let's do this with the first article that we have. And we can see there are each of those 3 images, but now displayed on a subplot in one figure. Now, there's something a little odd right here, right? So IamShow is completely ignoring the size of these images, right? You can tell this one right here, it's say 300, almost 400 pixels by almost say 700 pixels. This one is 120 by 100, almost 200 pixels, and this is only 75 by 75 pixels right here. I'd really like for those to be displayed the way that something that reflects the actual resolution of the images. And the way that we can do that is, instead of using subplot, we can use something called grid spec with subplot. So the way that this works is it says, okay, we'll do everything that we had before. So I'm going to import grid spec, and I'm going to grab the images. But now I'm going to create this what looks like a cryptic vector right here for each of the images that's inside of this, for each image inside of the images list. I'm going to go in here, I'm going to say, okay, well, how many columns and how many rows are in that image? Multiply that together, take the square root, and then round it to be an integer. So it's basically like saying, okay, I have this image. Well, how many rows do I have? How many columns do I have? Let me multiply those together and take the square root, which, if I had a square image, would basically give me the number of rows or columns that I have for that image. But it's basically taking the square root of the image size and rounding it to be an integer. And so what that allows me to do is actually put together a grid spec where I give it the number of rows that are in each of the, it's a ratio of all the widths. So I'm going to basically say, okay, I'm going to create a subplot, which is 1 by 3. And I would like to manipulate the ratio of the widths of each of those subplots. So now when I create this figure, I'm going to say, oh, okay, it's 1 by 3. So I have 1, 2, 3. But now the ratios are going to be equal to this rows vector that I just created. So if I have a small image, it will only allot, right? So let's say it was 10, 20, and 2, right? Basically, 10 right here, I would get something that was twice the size of the 10, and the 2 right here, if 2 was the very last value inside of rows, if this was my rows vector, it would probably be more like this, is what it would end up doing right here. Right, so it'll create these 3 subplots, but then this will be 10 rows, this will be twice the size of that, and then this will be only 1/10 of the size right here. So if the images themselves are much, much bigger than each other, I'll be able to see that inside of these subplots. So let me run this on the article. And we can see, yes, so now we have a true representation of the resolution between these different images from one another. And they're displayed actually quite nicely. So we can see the middle image is the biggest one, there's the second largest, and then the smallest thumbnail is over here. And again, you know, we can do this for every single article that we have. So if I define this function called plot all and just repeat everything that we just did above, right here, where I basically go in and say, okay, well, you know, give me the images, plot them according to the grid spec that I had, and now create a title for this figure, which is, oh, a.getRecurse, grab the main headline from the article, right? So I'm accessing a function from the superclass of my NYArticle class and setting that to be the title of the figure that we're going to display. So if I run this, what is going to happen is I'm going to create a bunch of articles, every single article that I have, and then for each of those articles, I'm going to plot all of the image data inside of a new figure for each of those, right? And so it's going out to the internet, it's grabbing all of this data, and it's saying, okay, well, here's the first article, here's the image data in the second article. Well, the third article that we had right here actually had only one image inside of it, so it was a variable length multimedia. And then here are the 3 images associated with the final article. We can see the thumbnail down here at the very bottom. Right? So that's a very kind of succinct way now that we're able to capture a bunch of image data and save all of that image data inside of inside of a Python list and display it however we want. So, of course, we probably want to do some data processing to the images. So let's do that. Let's go in here and I'm going to say skimage. It actually has some feature extractors inside of it. We won't go into detail on what those are, but essentially it allows us to take an image and run, for this one, we're going to take the histogram of ordered gradients, the HOG or HOG features. And that's essentially what it does is it looks at very distinct lines that are in an image and it says, okay, well, what direction are those lines moving? So it'll kind of take an image that we have right here and it'll go patch by patch and say, oh, okay, well, you know, how many, let me look at all the edges and which direction all of those edges move in for each of this article. And that turns out to be a pretty good representation for images themselves. You don't have to understand that completely. All that we're going to do right here is we're going to create a vector of features based on this image data that comes back. So I'm also going to convert RGB to gray images because that's what the histogram of ordered gradients really works on. You can do it on color images, but it's harder to do. So what I'm going to do here is I'm going to say, okay, enumerate all of the images from this article. For each of those, if the image is not equal to none, create a grayscale version of that image and resize it. Right? So I'm going to convert it to grayscale, and then I'm going to resize the image to be 25 by 25. And the only reason that I do that is so that each of the, so I'm going to be resizing each of these images that comes back here to be a 25 by 25 image. And then I will take the histogram of ordered gradients. And the reason that I do that is so that I can take the same number of patches inside each of those images. And eventually what I want to do is compare those images to one another. So I'm going to create this temp vector right here. It's empty, and I just append the gray images onto it, and I return temp right here. So for each of the articles, what I'm going to do here is I'm going to create this features array, and I'm going to add on to this features array. I'm going to say, okay, for this article, extract all the features and add it as a list into features right here. So essentially what is happening here is I'm taking this image data, I'm converting it into a 25 by 25 pixel image, no matter what the size was. And then I'm calling histogram of ordered gradients on that to turn it into a vector right here. So this is just a vector of numbers that describe that image, specifically describes edges that are in that image. But I'll do that for every single article. So I'll take this article, convert it to the exact same size, run that, and I'll get another vector, the exact same size as the vector that was there before, right? And so I can resize all of the images from the articles. And essentially this features plus equals. So features starts out as a empty list. But every time I call extract features, these features that are created get added on as separate rows inside of this features list. So features at the very end of this would be a Python list of all of those histogram of ordered gradients features for each of the images inside of each of the articles. Just like that. And so the very last thing that I'm going to do here is called NumPy vertical stack all of those features. So instead of being a Python list, or instead of having this be a Python list, I'm just going to turn it into a matrix of all of the different values, but it still represents these guys. This is hog for article 1, article 2, all the way down to however many articles I have. So articles of n right here, all of the image data that I have right there. So let me do that. I'll run that. It runs really, really quickly. It's very easy to resize these images and take the run this feature extractor upon them. So now we've converted our images into features. And now all I want to do here is take the pairwise distances between these features. So essentially what that does is it says, okay, well, let me take the distance between A1 and A2. And let me take the difference between A2 and AN right here. And it's going to create a totally new vector, sorry, a new matrix around here. So if I've got this as A1, let's say this goes from A1 to A3, we'll keep it simple. Then the pairwise distances that it's going to say is, okay, well, what's the difference between A1 minus A1 right here? So A1 subtracted from itself, right? That'll be, something very close to 0. Should be 0. Then it will be, okay, well, what's A1 minus A2 right here? And that'll be a new element inside of there. And, I can just take, so I'm just taking the pairwise distance between these two vectors. And then A1 minus A3 right here. So 3 elements on the row. And then same thing down here. This will be A2 minus A1, A2 minus A2, A2 minus A3, and et cetera for A3. This will be A3 minus A1, A3 minus A2, and A3 minus A3 on that. So I'll have each of these being, I'll get a 3 by 3 matrix on the output, right? So however many images I have, that'll be this right here. That'll be the length. I'll have 3 images, 3 by 3. If I had 5 images, this would be 5 by 5. And what that's telling me is what's the difference between those images, where lower means that the images are much closer to one another. So if I run this and we visualize that matrix right here, what I'm going to see is I've got all of these zeros on the diagonal, and apparently I wrote this in a way that was transposed. So what it actually did was all the diagonal elements are along this right here. So just kind of flip that in your head. But essentially what it's telling us is that so if this is article 1 and this is article 2, it's saying, well, those are actually really, really similar to one another. They both have low values, right? So A1 to A2, the distance between those images is not very far, versus all the other images they're pretty far away from, right? And it says it's also moderately close to this image right here, but not a whole lot. And so if we look at the first 3 images that it looks at, well, it's actually looking at the images from the very first article. So it's saying, oh, these images right here are extremely close to one another, and they're not really all that close. to this image. And that makes a whole lot of sense. These are identical images to one another, but this is actually just a snippet from that, which we would expect to have some different features. We would also expect the same thing to happen. So the next 3 images, we would expect these to be extremely close to one another, and maybe slightly similar to that as well. The third, after that, it gets an image that shouldn't be similar to anything. And then we should see the same structure for the last 3 images. So let's look at that. So the first 3 images are right here, and they're really similar to one another. And then that other one right here that we had of the Olympic emblem, it's not really close to much anything. And then the next 3 images that we have right here, well, the first 2 are close to one another, and they're somewhat close to the third one, but they're still, not as close as they are to one another. Then we have that image which didn't have anything that was close to it, and it's just far away from every single thing. It doesn't have a close distance. And then finally, the last 3 images, they follow the exact same structure right here, where the thumbnail is not all that close to the first 2 images. So that really concludes what we've been working on. So I think that we've been able to take what we know about Python, use it to scrub the internet, look at the New York Times, bring down some images, and then actually do some very, very simple data analytics on top of these images. But hopefully what we've done right here is really we've been able to create an intuitive interface to be able to access all of those images in an object-oriented way, such that each article was an object, and each multimedia entry that was part of that article became a list of objects that were inside of that article as well.